Good morning, dear students. We are going to see in this video Euler's theorem and corollary. Our first one we saw the basic concept of partial differentiation, how to differentiate partially. Second one we saw partial differentiation of composite function. And now we are going to say one important concept related to partial differentiation, that is Euler's theorem and corollary, and for that what we need is homogeneous function. So first let's see what are the homogeneous functions. Now if I have, say z is function of x and y, z is function of x and y. Now from this if we find z of tx ty, means replacing x by tx and y by ty, by this if we are getting t raised to any power into back z, then we say z is homogeneous of degree n. Let's have an example. If I have, say z is x cube minus y cube upon x square plus y square, this is our z. In this case, if I want to find z of tx ty, just replace x by tx, y by ty. You can see here t cube is common. We are getting x cube minus y cube. Same way here t square is common. We are getting x square plus y square. Mean this is t into z. So we will see here z is homogeneous function of degree 1. This one means this part. Let me have one more example. If I have z is, say x square plus y square under root upon x plus y. And now if I find z of tx ty, replace this by tx, this by ty, we have t square common inside root. So outside root it is t is to 1 into x square plus y square. Same way here, t is common, I am getting x plus y, this t is cancel. What we are getting is back only z. So what can you say about this? It is z, means we can always write it as t raised to 0 into z. Anything raised to 0 is 1, all of you know it. And so we are getting here, this z is homogeneous of degree 0. So this was homogeneous function. I will give one more example to get clear what is homogeneous function. Like if I have now z is sine of x plus y, and try to find z tx ty. Z tx ty will be, again put here tx ty, t is common, we are getting this. But see properly here, we cannot take t out. That's we cannot write t raised to some power into sine of x plus y. Means obviously this is not homogeneous. So for homogeneous what we need is, we must get it in the form t raised to any power into back z. That power may be an integer, positive, negative, maybe fraction, negative fraction, whatever. But we must get in the form t raised to z into back z. So this was homogeneous function, and now I will tell you what is Euler's theorem and the corollary. What we are going to see is main Euler's theorem, and then there are 3 corollaries which we are going to discuss. So in this video we will have Euler's theorem and the first corollary, and the next video we will see the next 2 corollaries. So let's first see what is Euler's theorem. Now this Euler's theorem and the first corollary will discuss together. They are much more similar. So first I have Euler's theorem. This states as, if z is a homogeneous function of degree n. What is the requirement? Z should be homogeneous function. Then the expression x dabba z by dabba x plus y dabba z by dabba y is equal to n into z, and the corollary 1, let me write and I will explain both the things again. Corollary 1 says if z is a homogeneous function of degree n, then x square dabba 2z by dabba x square plus 2xy dabba 2z by dabba x dabba y plus y square dabba 2z by dabba y square. This is n into n minus 1 into z. Now first I will explain this two statements with the help of simple example, then we will solve one problem. Now listen here. Let's have a simple example. If I give you z is x square plus y square. Say for a time being we don't know what is Euler's theorem or the corollary. I will ask you this expression, find x dabba z by dabba x plus y dabba z by dabba y. What is the procedure? The procedure says we want to find dabba z by dabba x and differentiate z with respect to x partially, multiply by x. Same way, find dabba z by dabba y, multiply by y and add them. Exactly same way when you go for this. Find dabba 2z by dabba x square means first we want to have first derivative, again differentiate second derivative. Same way here, same way here. So overall we need to find here 5 to 6 derivatives, multiply, add, etc. But just see how this Euler's theorem makes it very easy. If I have this example, simple one to understand, and we want to find out this expression. Everyone knows dabba z by dabba x is 2x, multiply by x, it will be 2x square. Dabba z by dabba y is 2y, multiply by y is 2y square. So we have 2x square plus 2y square, 2 common. Verbally you can say it is 2 into x square plus y square. But if I want to use Euler's theorem, what Euler's theorem says? First of all, we have to prove it is homogeneous. Now for that I will change my example because it's very simple. Now if I take some example of this type and I am asking you the same, we need to find the first derivative, multiply by x, then derivative with respect to y, etc. And you can see it's tedious here to get the derivatives, whereas especially for this expression it's more tedious because after finding dabba z by dabba x, again we have to differentiate. Here also we have to differentiate twice, same way here, and the problem is tedious. But if you use Euler's theorem, see, it becomes easy. What Euler's theorem says? It says, I'll just prove the function given z is homogeneous. And what to do for that? To prove homogeneous, what we need to do? Replace xy by txty. Once you replace them by txty, you can see here t square is common. We are getting x square plus y square upon, here see properly, t cube is common inside the root. So outside the root it is t raised to 3 by 2 into, we are getting x cube minus y cube. So I hope you all are getting me what I have done. When this is t raised to half into, see what we are getting, this part. This is nothing but our z. So we are t raised to half into z, and that gives us z is homogeneous of degree half. Now the moment you see it is homogeneous of degree half, what is our Euler's theorem statement? It says this expression is equal to nz. So for this problem, what we are going to get? We are going to get this x dabba z by dabba x plus y dabba z by dabba y, which was nz. It will be simply half into z. Means it will be 1 by 2 x square plus y square upon x cube minus y cube under root. Means actually if you find the derivative with respect to x, multiply by x, then derivative with respect to y, multiply by y, add, you are going to get this answer. But Euler's theorem has made it very easy. Just in 1 or 2 steps we are getting the answer. And similarly, the second expression which we want to find out, as I said again, for this expression, instead of finding all its derivatives, just check it is homogeneous. If you get it is homogeneous, then this expression is n into n minus 1 into z. For our case, our n is half. So for this problem, we are going to get whatever is this our second expression by using the corollary 1. In this case, our expression which is n into n minus 1 into z will be half into half minus 1 into z, and what we are going to get is minus 1 by 4z, which is minus 1 by 4 into x square plus y square upon root of x cube minus y cube. So this we got. I will just write the reason by Euler's theorem, and this we got by using corollary 1 to Euler's theorem. So this was just a simple example to illustrate this statement. Once again I will tell you one thing. Say if you are asked instead of x dabba z by dabba x plus y dabba z by dabba y, if I ask you a minus, or here if I ask you 2xy square, then we don't have any choice. We have to actually find the derivatives, multiply, add, etc. So remember these two expressions. The moment you see these two expressions, our first job is to check z is homogeneous or not. If it is homogeneous, this is n into z and this will be n into n minus 1 into z. That's it. That's the Euler's theorem and corollary. So again I am telling you that remember these two expressions. The moment you see these two expressions, you have to think of Euler's theorem and corollary means you have to prove the function is homogeneous. Rather, I will say you have to check the function is homogeneous or not. If yes, directly write this as n into z, this as n into n minus 1 into z. If no, what to do? We will see slowly. Let's have one more example. Now I will give the example where we need to find the expression whatever I gave you, but the function is not homogeneous. So if I have, say, z equal to x square minus y square upon x cube plus y cube plus 2xy. Now for this function, my question is find x dabba z by dabba x plus y dabba z by dabba y and x square dabba 2z by dabba x square plus 2xy dabba 2z by dabba x dabba y plus y square dabba 2z by dabba y square. Now again the moment I say I need to find these two expressions, the immediate thought must be I need to check if it's homogeneous or not. If yes, first expression is n into z, whatever is the degree of z, and second expression will be n into n minus 1 into z. Now look at this and you can check verbally. When I replace x by tx and y by ty everywhere, here what we are getting 1 by t into this, whereas here I am getting t square into this. Means this entire function is not homogeneous. So when our problem is the entire function is not homogeneous, first thing I will tell you, observe, is it combination of some homogeneous functions? What I mean is, you can observe, if I consider only this much, you can see this much, this is homogeneous of degree minus 1. Same way, replace this by tx, this by ty, here t square is common, here t cube is common. What is left with us is 1 by t, that is t raised to minus 1. So I have this is homogeneous of degree minus 1, whereas this is homogeneous of degree 2. So though z is not homogeneous, it is written as sum of two homogeneous functions. So we will use it and we can solve this problem as I will have, let u is x square minus y square upon x cube plus y cube and v is 2xy. Then two things you can see. First of all, I have z is u plus v and because z is u plus v, what I will get? X dabba z by dabba x plus y dabba z by dabba y will be x dabba u by dabba x plus y dabba u by dabba y plus x dabba v by dabba x plus y dabba v by dabba y, because you know sum of derivatives is derivatives as sum. So this is as good as two problems and just add them and nothing else. So first I will do it for u, then for v, and I will add it. Now while doing for u, look at this u. The similar procedure we will have. We will have whatever is given, or we have taken it as u. So consider, say u is x square minus y square upon x cube plus y cube. Now this gives us our usual procedure. What we are doing? We are finding u tx ty, and just now I explained you, it is t raised to minus 1 into u, and that gives us u is homogeneous of degree minus 1, and because it is of degree minus 1, we have x dabba u by dabba x plus y dabba u by dabba y. This is nu by what we have? Euler's theorem, so which will be minus u. Now next part I'll just explain, and you all will able to complete it, like how I got this is equal to minus u because it's of degree minus 1. Exactly same way, when I want to find out this part, just see what is degree of v. You can do it even verbally, or v is 2xy, so that gives us v of tx ty, 2 into tx into ty, so we are getting t square into 2xy, means what we have? V is homogeneous of degree 2. And now all of you please complete this. This is of degree 2, so obviously our this expression will be 2 into v. So we have proved this was minus u, this was 2 into v. So this entire expression which we want to find out, that will be minus u plus 2v. Minus u plus 2v means it is minus of x square minus y square upon x cube plus y cube plus 2 into, this is our v, that is 4xy. Means actually if you try to find out all these derivatives, dabba z by dabba x multiplied by x, dabba z by dabba y multiplied by y, for this entire and add it, you are going to get this answer. So you can see Euler's theorem has made it so easy. And now the second part, it's exactly similar, so I think I can leave it for you. At same way, this will be nothing but this expression for u plus this same expression for v, and just now we proved u is homogeneous of degree minus 1. So this expression for u will be minus 1 into minus 1 in minus 1 u, because what was our corollary one? This expression is equal to n into n minus 1 z. So I am using the same only for u. So for u this expression will be 2u, and same way when you are finding for v, v is homogeneous of degree 2. So that will be 2 into 2 minus 1 v, that is again 2v. So this entire expression is 2u plus 2v, and we are going to get 2 into u plus v, whatever is your u plus whatever is your v. And if you actually calculate all these derivatives, derivative with respect to x, again with respect to x, multiply by x square, here y, then x, multiply by this, same way here, add it, you are going to get back this answer. And see it, Euler's theorem has made it so easy. So again I am telling you at the end of this lecture, like whenever you want to find out this expression or this expression, just try to prove u is homogeneous. And once you get it is homogeneous, for this expression is equal to n into z. For this it is n into n minus 1 into z. If it is not homogeneous, first case I told you, maybe it is sum of two homogeneous functions, then it's just as good as two small problems you are solving. Find it for this and add. And next lecture we will see it's neither homogeneous nor it is written as sum of two homogeneous functions. Still we want to find this expression as well as this expression. What to do? Do we really have to actually find out these derivatives? No. We have for that corollary 2 and 3 of Euler's theorem, which will again make this very easy. So see you this in next video. So goodbye till then. Thank you very much.